In this presentation, we are going to discuss about the process synchronizations in operating systems. The outlines are background, the critical section problem, Peterson solutions, hardware support for the synchronizations, text locks, semaphones, monitors, liveness. The objective is describe the critical sections problems and utilize a race conditions. Extract hardware solutions to the critical sections problems using memory barriers, compare and swap operations and atomic variables. Demonstrate how mutex locks, semaphones, monitors and the conditions variables can be used to solve the critical sections problem, and evaluate tools that solve the critical sections problems in low, moderate and high convention scenarios. Background: process can execute concurrently, may be interrupted at any time, partially completing executions. Concurrent access to shared data may result in data inconsistency. Maintaining data consistency requires mechanisms to ensure the orderly executions of operating process. To illustrate is problems when we consider the bounded buffer problem with use of the counter that is updated concurrently by the producers and consumers, which lead to race conditions. So the race conditions consider the process P0 and P1 are created, the child process using the fork system call. So the race conditions on the kernel variable next available period time, which responds the next available period time. So unless there is a mechanism to prevent process P0 and P1 from accessing the variable next available period, the same period would be assigned to two different processes. So based on the next available period, it can be allocated to execute. The critical section problems consider a system of n processes P0 to Pn-1. So each process has a critical section segment of code where the process may be changing common variables, updating tables, writing files, etc. When one process in critical sections, no other may be in its critical sections. So critical sections problems is to design protocol to solve this. Each process must ask permissions to enter critical sections. In entry sections may follow critical sections with exist sections and then the remainder sections. So in this critical sections problems is solved by, if it is check the process is in the true state, it go to the entry sections, then the critical sections is solved, then go to the exit sections, then the remaining sections are executed. So in this critical sections problems, the requirements to use to solve the critical sections problem that are mutual executions, progress, bounded waiting. So in this mutual executions, if the process Pi is executing in its critical sections, then no other process can be executing in their critical sections. The progress time, if the process is in the executing in its critical sections and there exists some process that wish to enter its critical sections, then the sections of the process that will enter the critical sections next cannot be postponed indefinitely. When it's going to the bounded waiting, time, a bound must exit on the number of times that other processes are allowed to enter here. Critical sections after the process has made a request to the enter its critical sections and before that request is granted. So the interrupt based solutions are entry sections, disable interrupts. In these existing sections, enable the interrupt. So will this solve the problems? Yes. What if the critical sections is code that run for an hour? Can some process strains? So never enter their critical sections. So what is if there are two CPUs? So the first solutions is two process solutions. Assume the load and store machine language instructions are atomic, that is cannot be interrupted. The two processes share one variable in turn. So if it is in turn value, so the value to be set to that particular stage. Then algorithm for the process P. It is in true going to the particular critical executions, otherwise terminate that sections. So correctness of the software solutions, mutual exclusions is preserved. PI enters critical sections only if turn is equal to I, that is to be set. Okay, so and turn cannot be both 0 and 1 at the same time. So what about the program requirement? What about the bounded waiting requirement? That is the Peterson's solutions is essential. It has two process solutions. Assume that the load and store machine instructions are atomic. It has two variables, turn and boolean variables. So here two variables are set. Okay, so the turn and the boolean variables are used to correct that situations. So the correctness of Peterson's solution is provable that 3 CS requirement are met. Actually, the correctness solutions have 3 CS requirements. The first one is mutual executions is preserved. The second one is progress requirement is satisfied. The third one is bounded waiting requirement is met. The memory barrier, here the memory models or the memory grantees a computer architectures make to application programs. Memory models may be either strongly ordered or weakly ordered. So the example, returning to the examples of the slides, here we would add a memory barrier to the following instructions to ensure thread 1 output 100. Thread 1 now perform the memory barrier. Thread 2 now perform the memory barrier with the flag value is true. If thread 1 we are guaranteed that the value of the flag is loaded before the value of 5. For the thread 2 we ensure that the assignment to X occurs before the assignment flag. So the synchronization hardware. Many systems provide hardware support for implementing the critical sections code. Uniprocessor would disable interrupts. So currently running code would execute without preemptions. Generally, too inefficient on multiprocessor systems. The operating systems using this is not broadly scalable. So, the hardware support is essential in the above three format. to hardware instructions and atomic variables. In this hardware instructions, a special hardware instructions that allow us to either test and modify the content of the word or swap the content. So that can be explained or elaborated by the test and set instructions and compare and swap instructions. In the test and set instructions defined by the Boolean return value, where if its testing case isn't true, it returns the value is RB. The properties are executed automatically and returns the original values of the past parameters, set the new values of the past parameters to true. The solutions of using the test and set shared Boolean variable log initialized to false. So that solution is while this test and set value isn't true, the log is equal to false. So it's in the remaining sections. Then the compare and swap instructions. So it is defined by the compare and swap functions. So it return value is an integer and it get the value and expected value and the new value. So using this it return the temporary value if the temporary is a value. So these properties are executed automatically, returns the original value of the first parameter values. So the solutions using compare and swap is shared index log initialized to 0. That solution is while it isn't true, it moved to that comparisons of the compare and swap value. So if it is an log is 0, it is to the remainder executions. So next one is mutex logs. Previous solutions are complicated and generally inaccessible to application programmers. So the designers build software tools to solve critical sections problems. So simplest to mutex log. So it is a Boolean variable indicates if log is available or not. Here the protect a critical sections by the first acquire functions and then release functions. The call to acquire and release must be atomic. So usually implemented by the hardware atomic instructions such as compare and swap. The next tool is semaphore. The synchronization tools that provides more sophisticated way for browsers to synchronize their activities. The semaphore as integer variables can only be accessed via true invisible using the wait and signal function. Then the monitor is the next tool for the synchronization, a high-level abstractions that provides a convenience and efficient mechanisms for the process of synchronizations. The liveness here, the process may have to wait identify while trying to acquire a synchronization tool such as mutex clock or semaphore. So the liveness refers to a set of properties that the systems must satisfy to ensure the process make process. Okay, thank you.